Welcome back, students. In this lecture, we will be talking about conversion factors and using conversion factors to solve word problems in this class. And we'll end up with a discussion on density, which you can also apply conversion factors to solve. Many times in chemistry and in your health fields, you may want to convert from one unit to the next. Even in our everyday life, we have the need to convert from one unit to the next. Like for example, if you are following some recipe written in milliliters, but you only have cups at home, how would you be able to convert milliliters to cups? Or when you are traveling, let's say outside of the United States, and you look at speed signs that says 105 kilometers per hour, for example, you need to be able to convert that to miles, or vice versa if you have to convert from miles to kilometers. Of course, there are apps now that can do this for us, but let us see what is the math that lies behind these conversion problems. So let's start our discussion with the definition of a conversion factor. A conversion factor is a fraction that is derived from an equality or a ratio. So for example, the equality of 1 hour is equal to 60 minutes. You can write as a conversion factor of 60 minutes over 1 hour. Now, for every equality, you can write two conversion factors, and they are just reciprocal of one another. If you just put the numerator and denominator and flip the two, you will have a pair of conversion factors. Sometimes you want to use one, and some other times you want to use another. You will see what I mean in a couple of minutes. A special note is that you always want to include units when you are writing your conversion factors. So where can conversion factors come from? They can come from metric conversions. What we saw earlier from 1 hour is equal to 60 minutes. That is a metric conversion. Another example of that is when you have prefixes. For example, going from grams to kilograms, what is the equality between grams and kilograms, and you can write a conversion factor from that. You can also get conversion factors when you want to convert between the units of the metric system versus the English system. You can also get conversion factors from rates, dosages, ratios. And finally, you can get conversion factors from percentages, which is basically a ratio, but it's quite special, so we will leave it out as its own. So we will go through all of these examples one by one to illustrate to us how you can write conversion factors from equalities. First, let's talk about conversion factors from metric equalities. As an example I gave earlier, if you have an equality that says 1 kilogram is equal to 1,000 grams, you can write these two conversion factors. You can write 1 kilogram over 1,000 grams or 1,000 grams over 1 kilogram. Another example is an equality between centimeters and millimeters. Remember, centi means 100th, so 1 centimeter is equal to 100th of a meter, or 0.01 meter. So the equality that could be written there is 1 centimeters per 0.01 meter, or 0.01 meter over 1 centimeter. A special note about conversion factors from metric equalities is that significant figures do not apply to them because they are exact numbers. Another case where you can write conversion factors from is when you are trying to equate between a metric system unit and a US system unit, or the English system. For example, the equality between 1 kilogram is equal to 2.20 pounds can be written as 1 kilogram over 2.2 pounds and vice versa. The special note here is that between these two numbers, there's always going to be one number that does not have significant figures and one that does. Usually the one that has 1 in it, the 1 kilogram, does not have significant figures, for example. While the 2.20 pound does have sig figs and has 3 significant figures. It's trying to say that if you have exactly 1 kilogram, someone had to measure out how many pounds that was, and they recorded that only to the hundredths place in this case. Okay, so again, whenever you see or use metric to English system equalities, one side of that equality will not have sig figs and one will, and so your calculation will depend on that as significant figures. A special case is when an equality is an exact equality. So for example, 2.54 centimeters is exactly 1 inch, and that's by definition. So those are exact numbers. You do not have sig figs. Still, you can still write conversion factors from them. Right? So 2.54 centimeters per 1 inch, or 1 inch per 2.54 centimeters. Okay, again, sig figs do not apply because we are taking them from exact numbers. So here's a table of some common equalities you will use in this class. So as a review, remember that the metric conversion factors, none of these have any significant figures in them. None of these will have any significant figures. These do not have significant figures because they are, again, by definition. Now, when you go from metric system to the US system, you may have to consider significant figures. In this case, we have, for example, 1 meter, no sig figs here. How many inches is in 1 meter? Someone had to measure this, and they recorded to only the 10th place, so there's 1, 2, 3 sig figs there. 1 kilometer, in this case, into miles has 3 sig figs. And of course, this is just a significant figures as reported in this table. You may find other tables that have less or more significant figures. It just depends on where you're getting that information. You have to base your answer, of course, then on that information. As you see on this list, there aren't that many exact. There's only one that is exact. Now let's talk about conversion factors that are derived from rates, dosages, ratios, and the things like that. And these things often are found stated within a word problem itself, so you will kind of have to look for it. It's not listed on a table somewhere. Because it is found particularly in that problem, it only applies to that problem. For example, the speed limit is 105 kilometers per hour. So the equality there is 105 kilometers is equal to 1 hour. That does sound weird because we often don't think time is equal to distance, but it is true in this case. Since it is true in this case, we can write a conversion factor for it. We can write 105 kilometers over 1 hour and its inverse. Another example of conversion factors derived from stated problems is this, where it says 500 milligram tablet. Now, where is the conversion factor there? And when you see this kind of information, you have to know that that means it's 500 milligrams of something per tablet. So in this case, it's vitamin C. So you can write that it is 500 milligram of vitamin C per tablet, or 1 tablet is equal to 500 milligram of vitamin C. Oftentimes, when we want to recognize if a value in a problem is a conversion factor or not, there is a key word to look out for, and that's the word per. If you see the word per being used, it is often the conversion factor, because per often is used when you're talking about rates and ratios. Where is the significant figures in these problems? The sig figs are found in the values themselves. For example, 105 kilometers per hour, that's 105, that's 3 sig figs. In the 500 milligram per tablet, that's 1 sig fig because that 5 is significant, where those trailing zeros are insignificant. And lastly, you can get conversion factors from percentages. If you break down the word percent, per is, there you go, that keyword per is a fraction. So percent means out of 100, right? So it's an X number of parts over 100 number of whole. So if it's 5%, it's 5 over 100. So here's an example. An 18 carat gold ring is 75% gold. Okay, when you see percentage and you want to write conversion factors, you should say parts over whole. What's the part and what's the whole? If I am talking about 75% gold, gold is the part. And what's the whole? In this case, the whole is the ring itself. So you can say 75 parts of gold over 100 parts whole of a ring. Now, to write a proper conversion factors, you must have proper units. Gold and rings, those aren't units really. So instead, we write 75 grams gold per 100 grams of ring. Now, the unit that you choose doesn't matter. Notice that gram and gram will cancel each other out. As long as you have the right As long as you have the same unit, it doesn't matter what unit you use. You can use kilogram gold over kilogram ring. You can use pounds gold over pounds ring, tons gold over tons ring. All right, so as long as you are consistent on top and bottom, you're good. Of course, you can also have the opposite, the inverse conversion factor. Let's talk about sig figs in here. 75% gold means that you have only two significant figures here. The 100 is never considered in counting sig figs. All right, let's have a checkpoint. Can you write the correct conversion factor for a carrot that has 0.16% fat? That's very little fat. So 0.16% fat. So the parts is fat and the whole is carrot, correct? So it has to be 0.16 of fat per, that's the over sign, cent over 100 of carrot. Again, it's not a conversion factor if we do not write in proper units, so we can choose any units. And looking at our answer choices here, we see pounds as being the only unit used, so we can say it's 0.16 pounds of fat per 100 pounds of carrot. So the answer would be A. Notice that answer B is very similar, and indeed a lot of students will make that mistake and put B because they think 0.16% it can be written as 16. Don't make that mistake. Okay, now that we have mastered the skill of writing conversion factors, let's put them into use. How do we use conversion factors? Here's the mantra in solving word problems in chemistry. The given unit times the conversion factor is equal to the needed unit. If you have that mantra down and always apply it, you will always get the right answer. Of course, the trick is then to figure out what's the given unit and what's your conversion factor and what is needed. Because sometimes you may use more than one conversion factor. Okay. Now you may know other ways of solving problems from your math class, for example, and that's a great thing if you have that tool. But I want you also to learn this method of solving problems, the method used in chemistry. It may not seem that important in these kind of problems I'm throwing at you, but later on, halfway through the semester when we're actually solving chemistry problems, they actually become very useful, and your old method of solving problems similar to this will complicate things. So this method of solving problems in chemistry is called unit analysis or dimensional analysis. So we are being guided in our problems based on the units. Another term for that people use is dimensions. So let's take a look at an example. It's stated here how many hours are in 155 minutes. Again, you can solve this in any way you want to from your math class, but let's solve it from the unit analysis way. In this way, we have to identify again the given, the needed, and the conversion factors. Let's start out with what is the needed. How many hours are in 155 minutes? The thing that is being asked of you to calculate is your needed, is hours. The given is the situation at hand, which is 155 minutes. In this case, there are no conversion factors stated explicitly in the problem, but in order to go from minutes to hours, you have to use something that relates hours and minutes, and so the conversion factor that we know from the table is there are 60 minutes in 1 hour. After we have identified the given, the needed, and the conversion factors, let's put those into our mantras. The given times the conversion factor is equal to your needed. So let's see if that works here. Your given is 155 minutes times your conversion factor is equal to your needed. But as you do this math, you realize it doesn't make sense. This is where unit analysis comes in. If you just focus on the unit for now, you will see that the minute will multiply with the minute divided by hour gives you a very funky unit. That unit does not make sense. Okay, so this is not the right approach. And this is where the other conversion factor comes in. Remember, for every equality, there are two conversion factors you can write. So let's try this again. If we put 155 minutes times this new conversion factor, where the minute is now on the bottom, you will see that the minutes will cancel each other out. Remember, fraction means whatever on the top, multiply each other, divided by whatever on the bottom. So top and bottom, if they're the same thing, will divide to become 1, meaning they cancel out, leaving you only one unit left, which that unit is hour. All right, so you punch down your calculator and you get this number. And of course, we have to keep in mind when we write our final answer to have the correct sig figs. In our problem, 155 is 3 sig figs. Our conversion factor is exact, so there are no sig figs. So our answer should have, yes, 3 sig figs. So we have to drop that 3, 2.58 hours. Okay, let's recap again. Whenever we solve a problem, we need to use the given, multiply by the correct conversion factor. Remember, there's always 2 you can use. You can always flip-flop them until you get units to cancel out, and that will give you your needed. Again, unit analysis tells you that however you set up the equation, the only unit that is not crossed out at the end is the unit you need. If that's the case, then you have done it properly. That's how you're going to use unit analysis to guide you in this problem solving. Let's kick it up a notch and use conversion factors in multi-step problems. Okay, so let's read this example. A doctor ordered for 0.50 grams of Keflix, which is available as 250 milligram tablets. How many tablets of Keflix are needed? Okay. Now, if you have a fear of these word problems, just take a deep breath in and start identifying your needed and your given and your conversion factors. Okay. So, how many tablets? That's your needed, right? It's usually the question. How many tablets? So your answer should end in tablets. A doctor ordered for 0.5 grams, so that's your given. Another way of identifying this is saying, replacing given is the if statement and needed is the then statement. If 0.5 grams, then how many tablets? If the doctor wanted 0.5 grams, how many tablets do you need? You can kind of do that in many problems. Just replace what's the if. The if is a situation, right? What if this, what if that, then what? Okay, that is your what if monologue to yourself. And lastly, we have to identify the conversion factor. In this case, it's a 250 milligram tablet. Our conversion factor is a dosage, is 250 milligram Keflix per tablet. Okay, so we have identified it. Now let's just apply the mantra, apply the formula that we have learned. Given times conversion factors equal needed. The given is the 0.5 grams of Keflix, and you multiply that by the conversion factor, and you say, oh, they cancel out, and you should get your needed. But is that true? Right? It's actually not that simple, because here you're trying to say grams cancel out with milligram. Those aren't the same units. If some things aren't the same unit, do not cancel them out. They cannot cancel each other out if they are not the same unit. So it turns out we do need another conversion factor to connect us from grams to milligrams, right? Because right now we have something in grams and we have something in milligram, and we need to connect the two. The conversion factor we need is not necessarily given to us in the problem, but we have to come up with it or look it up on the table. So for example, in this one you wanted to convert between grams and milligram. You say to yourself, what's the relationship between milligram and gram? So 1 milligram is equal to 0.001 gram. Another conversion factor that some people like to use better is 1,000 milligram is equal to 1 gram. So either this you can use, and their inverse you can use too. It's whatever you are comfortable with. I like to go with this so that we are consistent throughout the semester, but some of you like to think about this already, so I'm not going to stop you. Okay, now that we have this conversion factor in hand, let's put it back in and solve this problem correctly. Okay, so notice that now we have grams and grams will cancel each other out. Milligrams and milligrams will cancel each other out, giving you only tablets in the end, right? So go ahead and we go ahead and do this problem where we just multiply everything on the top first. So that's 0.50 times 1 equal divided by 0.001 divided by 250. Make sure you know how to use your calculator properly to do that mathematical function. Now, if you have 2 in your calculator, then that's a good sign that your calculator and you are on the same page. Always check, always at the end, make sure if you have the right sig figs. In this case, looking back at our original problem here, we have 2 sig figs here and 2 sig figs here, so our answer should have 2 sig figs, and that turns out to be 2.0 tablets. Alright, so that's using conversion factors to solve multiple step problems. Let's see if you can do this on your own. Checkpoint here. Simethicone is a gas relief medication for infants. The recommended dose is 5.9 milligrams drug per kilogram body weight. Calculate the dose that should be given to an infant weighing 24 pounds. So again, pause this video and solve this problem. Alright, how did you do? So hopefully this was your setup, okay? Where you have start out with a 24-pound baby as your given. That's your if situation. If 24 pound, then how many dose? And the rest are conversion factors. You have to use as many conversion factors as you can until you reach only one unit left, and that unit is the unit of milligrams of drug. Okay, so doing this problem, first the body of the baby will cancel out, then the grams will cancel out, then the kilograms will cancel out, giving you milligrams of drug in the end. Giving you the answer of 64 milligram of drugs. For complicated problems like this, I also want to point out where students often make a mistake. A common pitfall in these problems is when students take shortcuts and don't write the complete conversion factors out. What I mean by complete is, for example, when you write 504 grams of body over 1 pound of body, not just 454 grams over 1 pound. Let's see how that can lead you astray. So for example, you may recognize like, oh, I have 24 pounds and I need to convert that into grams, so you go ahead and do that, leaving out specific grams of what. So from the gram, you say, oh, I need to go out to milligrams, so I convert grams into milligrams, so the gram and grams cancel out, giving you milligrams, and finally milligrams cancel out, giving you last with this canceling out with this conversion factor, giving you finally your units at the end and say, hey, there's only 1 unit left, and you either get confused at this point or you have written the wrong answer, because your answer will be in kilograms of drugs, and number one, that's probably not very safe in terms of health and medicine, but also not the right answer. So do be careful and write out the units fully in your conversion factors. Alright, so we will round out this lecture talking about density. Density is the ratio between the mass of an object to its volume. Another way of thinking about it is for every volume of an object, how much mass can be crammed into it. It's how tightly packed your object is, right? So when you think about something that has high density, it's very high, tightly packed. When something has low density, it's very lightly packed. There's a lot of space in between, right? The ratio between mass and volume or space is density. Since density is defined by mass divided by volume, its unit is also a unit of mass over a unit of volume. So oftentimes you will see grams per mil or grams per cubic centimeter. Now every substance has its own density. Some substances in different states have different densities. Let's start discussing about density by talking about the density of water as our benchmark. Water has a density, liquid water has a density of 1.00 grams per mil, while aluminum has a density of 2.7 grams per mil, and lead has a density of 11.3 grams per mil. Looking at this picture, where do you notice the position of the aluminum and the lead? Right, they are at the bottom. It turns out things that are more dense will sink in water, while things that are less dense will float in water. As you see here, you see that cork floating? Well, and that's because its density is only 0.26 grams per mil. How about that ice cube? What do you think its density should be? More or less than 1? That's right, the density of solid water, or in this case ice, is less than water, 0.92 grams per mil. That's why it can float. Let's take a look at the densities of some common substances. Let's just see what kind of pattern stands out. It's divided into solids, liquids, and gases, and in the solids, a lot of things tend to be more dense than water, tend to be more dense than 1. The metals, for sure, gold, lead, silver, copper, iron, all of these are very dense. Metals tend to be very dense. Okay? When you go to liquid, they tend to have the same density as water, except when you go to mercury, it has a high density. Well, it turns out mercury is the only metal that is a liquid, so it does have that metal property of being very dense. And when you go back to the gases over here, you may not notice it, but the units have changed. It's no longer grams per mil, but grams per liter. So now you have grams in a bigger amount of volume, so these are definitely 1,000-fold less than these, right? So yes, gases are not dense at all. And we'll talk more about this when we talk about properties of states in the next chapter. Now, these density numbers were measured by someone, and in fact, you can measure them because, again, density is basically mass and volume, and you can definitely measure mass and volume. So in this class, we will have an opportunity to measure a density of an object. So for example, let's think about this zinc cylindrical object here. To find its density, to remind ourselves that density is mass over volume, so we need to find the mass and the volume of that object. To get the mass is quite easy. You just go to the scale and find its mass. Okay, now volume, how would you find the volume of an object? One way to obtain the volume of an object is to use a formula. For example, if you wanted to find the volume of a cylinder, you can use this formula, where the volume of a cylinder is equal to pi times radius times its height. But let's say you have an object that is not defined by an equation like that, then how would you find its volume? You can do so by a technique called volume by displacement. In fact, even for regular objects, you can use this technique. And how does this technique work? First, you will need a graduated cylinder and you fill it up with a certain amount of water. You take a note of that starting volume of water, in this case is 35.5 ml. Then you put that metal piece or any object into that water and see how much water it displaced. Right? The amount of water is displaced is the amount that rose up after you put in the metal cylinder. The metal has a volume, and once it is in the cylinder, it displaces the water. So the water that it displaces is the same volume as itself, and that's a trick in finding the volume of an object. So in summary, the volume of the substance is equal to the final volume of the water minus the initial volume of the water in the graduated cylinder. So let's just use this problem and solve it. Again, let's state what we know. We know that a mass is 68.60 grams. This is a measured number from a digital scale, so all 4 numbers are significant figures, keeping that in mind. Then we find out its volume. You take 45.0 minus 35.5. This is a subtraction problem. Since this is a subtraction problem, we need to keep in mind to keep the same place value as the least decimal places. So in this case, it's the 10th place, so it has 2 significant figures. Plugging that into our density equation, mass divided by volume, you should get 7.2 grams per mil. All right, let's check our understanding with this checkpoint problem. Again, pause the video to solve this problem. All right, so how do you solve this problem? The question is, what is the mass of the lead cylinder? So we need to know mass. Density is given to us, 11.3 grams per mil, and we are given the process where the object will displace some kind of volume, so therefore that information gives us volume, right? To start these kind of problems, I like to usually draw it out. In this case, it starts out with 72.3 ml, and somehow an object displaced the water, giving a new volume reading of 86.7 ml. So we know from that the volume of this object is 14.4 ml. Going back to our original equation, density is equal to mass over volume. In this case, though, we are asked to find the mass, not the density. So we just need to rearrange this math equation. If you need to know how to rearrange equations, go ahead and go back to lecture 1 for the math review. After we have rearranged the equation, we get mass is equal to density times volume. So all we need to do is plug in density and plug in the volume that we have calculated. The density is 11.3 times the volume is 14.4 ml. Both of these numbers have 3 sig figs, so we should make sure our final answer does have 3 sig figs. Doing this on the calculator, we get 162.72. With 3 sig figs, we can round this up to 163 grams. Answer is A. Very good. Now there is another way in solving this problem. As you notice, density is grams per mil. You see that per right there, right? So per, again, goes back to our start of this lecture, is a conversion factor. So we can use density as a conversion factor in solving it like any conversion factor problem, where you have your needed, in this case the mass, and then the conversion factor, and the given. This is another way of setting up the problems, is setting up into cells, where the cells on top are the numerators and the cell on the bottom are denominators. The given is always put on the top cell as a numerator first, so we start with 14.4 ml, which is our given of volume. Multiply that by the density is 11.3 grams per mil. See how using this kind of cell separates the gram and the mil? So in the end, you can see that the mil and the mil really can be crossed out very clearly. That gives us 162.72 grams, just like in the last problem. So in any way you solve this, either in the previous way or as a conversion factor, is fine. And rounding out our lecture today, we will talk about specific gravity. Specific gravity is basically the relationship between the density of a substance and that of water, which is conveniently 1.00 grams per mil. Since we are talking about the ratio between the density of one and the density of another, the units of density will cancel out, giving specific gravity a value that is unitless. Again, let's take a look at this. Specific gravity is defined by taking the density of something, dividing it by the density of water. Since you are dividing by 1, you are not really changing the value. So when you are calculating specific gravity, you are essentially stating the value of the density of that substance again without stating its units. What I mean by that is, for example, if I ask you to find a specific gravity of gasoline, what would you say if you had the density of gasoline already? So instead of saying that gasoline has a density of 0.74 grams per mil, you would just say that gasoline has a specific gravity of 0.74. Again, no units there. So how do we do that? Let's apply the definition of the density of the gasoline divided by the density of water, giving you 0.74. The units have canceled out. Simple as that. Now, specific gravity is useful in the medical field. So that ends our lessons for today. So what have we learned, or what can we do by the end of this? We can first write conversion factors that relate to units, keeping in mind of their significant figures if they have any. We can also use conversion factors to change from one unit to another in solving word problems. And then lastly, we can calculate the density of an object and use the density to calculate the mass or volume of that object.